Lambert. Welcome everybody, and thank you for joining, especially at this time of the year where the holidays are going on. Let's learn a thing or two about steel today. So let's start with today's talk. So we'll start with briefly with a brief introduction to steel production, followed by an exploration of the various production processes, because there are many processes that differ actually. Then we will delve into the types of steel and see their unique properties before moving on to the actual industrial applications. We'll then discuss the environmental impact of steel production and the sustainability practices in this industry. To wrap things up, we'll have a quick exercise and finish with a Q&A session to address any questions that you may have. All right, so let's start with the introduction. So, first question, what is steel? Well, we know that steel is one of the most essential materials in modern life. At its core, steel is an alloy primarily composed of iron and carbon, with elements like manganese, chromium, or nickel added to enhance its properties. What makes steel exceptional are its characteristics, so high tensile strength, ductility, toughness, and its ability to be recycled indefinitely without losing quality. This combination of strength, versatility, and sustainability explains why steel is a cornerstone of industrial and structural applications worldwide. So, fun fact that steel can be recycled infinitely without losing its quality, which is one of the most attractive features of actually producing steel. All right, so let's talk about the ancient origins. So, steel has a rich and fascinating history that dates back to ancient times. So, early steel production can be actually traced to around 1800 BC in regions like Anatolia and India. One notable example is wood steel, celebrated for its exceptional quality and craftsmanship. Fast forward to the Industrial Revolution, the 1850s saw the development of the Bessemer process, which is a groundbreaking innovation that enabled mass production of steel. This process laid the foundation for steel's widespread use in industries that we now see today. In the modern era, advancements in techniques and technology have cemented steel's role as a critical material in industrial and commercial applications worldwide, symbolizing the progress and innovation throughout the ages. So, steel is indispensable to our modern world for several reasons. So, economically, it forms the backbone of industrial economies, generating millions of jobs globally and driving the industrial growth. Also, steel's versatility is evident in its applications across industries. In construction, it's essential for building structures like bridges, buildings, and roads. In transportation, it plays a pivotal role in the production of cars, trains, and ships. In the energy sector, steel is vital for wind turbines, pipelines, and infrastructure supporting renewable energy. Moreover, steel is a cornerstone of innovation. It has been integral to technological advancements, from constructing towering skyscrapers like the one you see in Dubai, for example, to enabling the development of high-speed rail systems. Steel truly stands as a symbol of strength and progress. All right, so now that we know a bit of steel, let's talk about the production processes and see how steel is actually being made. So I'll be focusing on the two most common steel productions, which dominate the industry. The first one is the basic oxygen furnace, or BOF in short, and the second one is the electric arc furnace, or EAF for short. So the BOF process refines molten iron from a blast furnace, combining it with scrap steel to produce high-quality steel efficiently, while on the other hand, the EAF method uses electricity to melt the scrap steel or other iron sources, offering a more sustainable approach, especially in the recycling. However, let's look at each process and study more about it. So, the first process, the BOF. So, what exactly is BOF process? So, it's a process that refines molten iron into steel by using a high-pressure oxygen stream to reduce the impurities efficiently. The key raw materials for this method include hot metal, which constitutes about 90% sourced from a blast furnace, and scrap steel, which makes up the remaining 10%. So scrap steel is basically the steel that's being recycled. The scrap steel also helps to cool down the molten metal during the process. And a standout feature of this BOF process is its speed. It can convert molten iron into high quality steel in under 20 minutes, making it very important or very fast for large scale steel production. Now, let's break down the key steps of the basic oxygen furnace process. The first step is actually charging the furnace. So the process begins with loading hot metal and scrap steel into the furnace. So imagine you have this huge pot where you start loading the hot metal and the recycled steel into this hot pot. Then the second step is actually blowing oxygen. So high purity oxygen is then blown into the molten metal at supersonic speeds. So this is very fast. This step is crucial as it oxidizes impurities like carbon, silicon, and phosphorus, forming a byproduct known as slag. Then, following this step, we have the refining step, which is after the oxidation, the temperature and chemical composition of the molten steel are adjusted to achieve the desired properties for the final product. And lastly, we have the tapping, which is in this step, the liquid steel is poured into a ladle for casting, while the slag, which contains the oxidized impurities, is left behind. So basically, we put the steel in the areas where we want to cast it, and this can be later processed for the desired product that we want. So all of these steps summarize the BOF process, which is a very highly efficient process for producing large volumes of high quality steel. With that being said, the advantages are, first, as we said, high efficiency. So the BOF process can produce large volumes of steel in a short amount of time, making it highly efficient for industrial scale operations. Also, its quality is very high, so high-grade steel can be produced, which are important for demanding sectors like the automotive, manufacturing, and construction sectors. And lastly is flexibility. So it can incorporate around up to 30% recycled materials, which can help improve sustainability. But of course, the EAF can integrate more, which we'll be talking about soon. All right. So as there are advantages, of course, there are also challenges or disadvantages of this process. First, the most important disadvantage, high carbon emissions. So a major drawback is its substantial CO2 output, largely due to the reliance on coal and blast furnaces, so the reliance on fossil fuels. This contributes to the steel's industry environmental footprint. Second, it's also energy intensive. So the BF process requires a large amount of energy, especially for the iron making and the oxygen production, which adds to the operational costs and also releases more carbon dioxide emissions because of the need of this energy. Because keep in mind, we are melting iron here, so the temperatures are very, very high. And lastly is the raw material dependency. So it's heavily reliant on iron ore and coke, both of which are finite resources, making it less sustainable in the long term. So these disadvantages underline the need for innovation and sustainability practices in steel production. All right, so let's take a look at this quick 1-minute video that shows or summarizes the BOF process. Dr. Lamed, could you please confirm if you can hear the video?
The basic oxygen furnace process is a method of steel making in which hot metal or pig iron is made into steel.
Yes, we can hear.
Perfect. All right. All right, so let's begin again. All right.
The basic oxygen furnace process is a method of steel making in which hot metal or pig iron is made into steel. In this process, either hot metal or pig iron, steel scrap, and flux or burnt lime is charged into a furnace called a converter or vessel. Next, oxygen is blown into the mixture using a water-cooled metal tube called a lance. Once the carbon level has been reduced in the steel, the lance is removed, and the vessel is emptied by rotating it to pour the refined steel into a ladle. The vessel is rotated in the opposite direction to pour out and discard the slag, along with the impurities it absorbed.
All right. So this is just a quick animation to give you a better idea of how the process works. So as we said, we have a huge furnace, and then the raw materials are entered inside the furnace. And this is how we have this process. All right. So now let's move on to the other process, which is the electric arc furnace. So this process primarily focusing on melting scrap steel or direct reduced iron using high-powered electric arcs, making it highly reliant on electric energy compared to the BOF, which doesn't use electricity. So the main input for the raw materials is scrap steel, which is recycled steel. Optionally, you can also add direct reduced iron or DRI for short, which is added for quality enhancement. This is basically a type of iron that's produced from another plant, which is added to improve the quality of the steel. The key features of this process is that it's incredibly flexible, allowing for smaller batch sizes and production of various steel grades. Importantly, it is more environmentally friendly compared to traditional methods with higher recycling rates and lower carbon emissions. So this combination of adaptability and eco-friendliness makes the EAF a crucial player in modern steel production. So let's talk about the steps in the EAF process. The first step is similar. We have the loading step, which is scrap steel or DRI, which is the direct reduced iron, is loaded into the furnace. This is the starting point, which is where the electric arc will be inserted. Then we have the melting process. So in the melting process, the high-powered electric arcs are generated between the electrodes and the scrap on DNI, melting the materials at extreme temperature. So imagine we have these electrodes that are inserted inside, and these electrodes produce electricity which heats and melts these materials at high temperatures. Then we have the refining process, which is the adjustments to the molten steel composition are made by adding alloys, ensuring the steel metal meets the specific quality and property requirements. So think of it like this, we're adding spices or we're adding some components to improve the quality of the final steel. Then we have the final step, which is tapping. And the tapping, the molten steel is poured into ladles for further processing, like shaping or casting based on our desired product. So these steps are basically summarizing the EF process. All right, how about the advantages? So first we say that this process has higher recycling capability, so it can utilize up to 100% scrap steel as input, making it very, very strong in recycling and reducing waste. So we do not need to add any virgin steel. We can just use scrap steel, which is recycled steel, to produce new products. It also has lower emissions, and this is because we do not use the fossil fuels like coal compared to the BOF process. And also, if the electricity is generated from renewable energy, then this will even make it a cleaner or greener process. It has a good energy efficiency because it uses electricity as its primary energy source, which means that EF processes can be integrated with renewable energy, as I said, making it a future-proof choice. And lastly, the flexibility. So the EF can adjust production levels to match the demand. So this gives good operational flexibility and also reduces the downtime. So these are some of the advantages of the EF process. As for the disadvantages, so it depends on electricity. So high electricity consumption means there's higher costs in areas with expensive or unreliable power, because every country would have different electricity prices. And so if the electricity is expensive, this might make the process less advantageous. There's also some impurities in scrap steel, so we need to ensure that the product is up to the demand by perhaps adding DRI. And then the lower production scale compared to the BOF, so it's less suitable for large scale production. And lastly, the electrode costs are expensive. So the graphite electrodes are expensive and they need to be maintained every once in a while. All right, so let's take a look at another quick animation to understand how the EF process works.
To start the electric arc furnace process, recycled steel scrap or other iron-rich raw materials are charged into the furnace along with slag-forming materials. Next, 3 large graphite electrodes send high-powered electric arcs through the scrap, generating temperatures up to 3,000 degrees Fahrenheit. At this temperature, the iron-rich raw materials melt into liquid steel, and a protective slag layer is formed. Once the steel has been completely melted, it is tapped into a ladle for further processing, and the excess slag is poured off in preparation for the next heat. EAFs are very popular when building new steel facilities because of their small size, lower cost, and reduced environmental impact.
All right, so as we said, that these processes are attractive because they are more environmentally friendly, and especially now with the 2050 net zero emission goals, I think that new steel production plants are always using the EAF technology. So this table summarizes the two differences. So we said for the input material, BOF uses primarily iron ore, coke, and some scrap, while EAF relies on scrap steel or direct reduced iron. As for the energy source, BOF depends on coal and oxygen for its operation, whereas EAF runs on electricity, making it potentially compatible with renewable energy sources. As for the CO2 emissions, the BOF has high carbon emissions due to the reliance on coal, while EAF has significantly lower emissions, especially if we use renewable energy for the electricity production. Then for the recycling rate, BOF has a limited recycling rate, as we said, around 30% of scrap steel can be used, whereas EAF can utilize up to 100% recycled materials. So this makes it even more eco-friendly. And lastly, for the production scale, BOF is ideal for large-scale production, while EOF offers flexibility for small to medium production scales. So this is also one of its you could say advantages, as it's quite flexible. All right, with that out of the way, now let's talk about the different types of steel that are being produced. So steel come in various types, each tailored to specific application and industries. The most common types include carbon steel, alloy steel, stainless steel, and then tool steel. So each type has unique characteristics that make it suitable for different uses, from construction to manufacturing and to different industries. And in the following slides, we'll dive deeper into each type and explore their properties and uses. So I know in this picture, they all look the same to you, but trust me, the properties differ from each type of steel. So let's talk about carbon steel first. So carbon steel is the backbone of steel production, actually, accounting for nearly 90% of all steel that is being made. Its key feature lies in its carbon as the primary alloying element, which directly influences its strength and flexibility. So there are three main subcategories. Low carbon steel, which is highly ductile and weldable, making it ideal for construction. Then we have medium carbon steel, which is perfect for machinery components. And lastly, we have high carbon steel, which is known for its hardness, suitable for tools and springs. The applications of carbon steel, range widely, especially on the type of carbon steel, from pipes and bridges to essential automotive parts. Its versatility makes it an essential material in numerous industries. Then we have alloy steel. So alloy steel stands out for its unique composition, containing elements such as manganese, chromium, nickel, or molybdenum. These additional elements allow it to be tailored for specific properties like enhanced strength, toughness, and wear resistance. So the common applications of alloy steel include gears, pipelines, and power generation turbines, where the durability and performance under stress are critical. Its primary advantage lies in its exceptional durability, as I said, and the resistance to corrosion, making it a go-to material for industries requiring reliability in demanding environments, so like power plants, for example. Then we have stainless steel, which I'm sure everyone here has heard or have heard about stainless steel. So stainless steel is a versatile material known for its exceptional corrosion resistance, achieved through a minimum chromium content of 10.5%. This gives it its attractive, polished appearance, which is widely recognized. So it can be actually categorized into three main subtypes. We have the authentic stainless steel, which is the non-magnetic and highly corrosion resistant, ideal for demanding environments. Then we have the martinistic, which is the hard and magnetic, commonly used in cutlery and tools, like the forks and knives. And then we have the ferritic, which is offering moderate corrosion resistance and is a more economical option. So the applications, they range from medical instruments and kitchen appliances to architectural designs. So it showcases that it's a very reliable and aesthetic steel that can be used in diverse industries. Lastly, we have tool steel, which is specifically designed to withstand high mechanical stress and elevated temperatures. So this makes it perfect for demanding applications. Its key features include the presence of elements like tungsten, molybdenum, cobalt, and vanadium, which provide superior hardness and resistance to deformation under intense conditions. So this steel is widely used in manufacturing cutting tools, dies, and molds due to its exceptional durability and toughness, which is why it's called actually tool steel, because it's used in a lot of manufacturing cutting tools. In industries where precision and strength are important, this tool steel stands out as a material of choice. It's because it's very reliable and very efficient even in the most rigorous environment. So let's just do a quick summary. So we said that carbon steel is known for its high strength, making it essential for like constructing bridges, buildings, and automotive parts. Alloy steel, on the other hand, offers enhanced properties like toughness and wear resistance, so it's useful for gears, turbines, and pipelines. Then we have stainless steel, which stands out for its corrosion resistance, which is why it's widely used in medical instruments, kitchenware, and even architectural designs. Then we have tool steel, which is for its hardness and temperature resistance. So it's useful for tools, dies, and molds. So we can see that although they are somewhat similar in their in their properties, each steel has its own key feature and its own industry where the steel will be very useful in. So this is why it's important to know that there are different types of steel uh, other than the normal, for example, stainless steel that we keep using in our daily lives. Now let's talk quickly about the industrial applications. All right, so we have four most common steel applications. First is construction, of course. Then we have the automotive sector. Then we have the manufacturing sector. And lastly, we have specialty products. So let's just quickly hover over each industry. So steel and construction. So steel is an incredibly versatile material with applications, as we said. In this slide, we highlight the construction. So we see that everywhere you see any construction, bear in mind that steel is 100% used somewhere. So it can be used in creating beams, columns, and frames for skyscrapers and bridges, as you can see in the photo. They also can be used for reinforcement bars, which are the bars that reinforce concrete in the buildings and the foundations. It can also be used for roofing and cladding. So it's lightweight yet strong steel, which is for the weather-resistant roofs. So why would we use steel other than other materials? It's because it has a high tensile strength. It's ductile and it also resists earthquakes. And it also has a long lifespan with minimal maintenance required. As for the automotive industry, it strikes the perfect balance between safety, performance, and cost. So it can be used for body panels. So low carbon steel is favored for its formability and durability, making it ideal for crafting the vehicle exteriors. Can also be used for the chassis and frames, which advanced high-strength steel is used to create lightweight yet robust structures, contributing to vehicle stability and performance. Can also be used for engine components. So alloy steel actually offers exceptional wear resistance, as we said, and thermal stability. So this can be used in the engine. And lastly, it can also be used for exhaust systems. So stainless steel is a material of choice in exhaust systems due to its superior corrosion resistance, especially against heat and moisture. So as I said, why steel in this industry and not other material? Well, first, it enhances the crashworthiness, so this ensures passenger safety. It also has provides fuel efficiency because it's very lightweight. And lastly, it's cost effective compared to other alternatives like aluminium, for example, which could be more expensive. In manufacturing, it also is very important. So the applications, as we said, could be tools and dies. So for cutting, stamping, and forming process, as you can see in the picture here. It can also be used for machinery, like robots, for example. It can also be used to make industrial machinery parts. And of course, the most important application is in our fridges, and our washing machines, and our stoves, so in appliances. So stainless steel is commonly used in a lot of these equipment or a lot of these machines that we use on the day-to-day basis. So why steel? Of course, we said it's high wear and fatigue resistance. It can handle high temperature and stresses, and it's also recyclable, which is very important to promote sustainable manufacturing. And lastly, we have steel and specialty products. So it can be used in medical devices. So I'm sure if you've been to the dentist, you can see that a lot of this equipment or in surgery, for example, that they use stainless steel. It also can be used for aerospace components because airplanes, they need a lightweight alloy steel, which can be useful, strong yet light to ensure the aerodynamics. And then in the energy sector, as we said, it can be used for the turbine blades. So the wind turbines, for example, they use a lot of steel. And lastly, it can also be used in consumer goods. So I'm sure some of your jewelry or watches are also made from stainless steel. So as we said, why steel? Because it's biocompatible. So for medical applications, we can use it to operate on humans with no issues. There's also superior resistance to corrosion and extreme conditions. And lastly, it also has an aesthetic appeal in consumer products like watches and so on. All right, so now let's talk about an important issue that surrounds the seed production, which is the environmental impact and also some of the sustainability practices. So seed production is very important, but it is also a very carbon emitting sector. So while it's critical for modern infrastructure, it also accounts for around 7 to 9% of the global CO2 emissions, making it one of the largest industrial contributors to climate change. So why is that? It's because emissions mainly stem from the combustion of fossil fuels, like coal in the blast furnaces, and from process emissions during the reduction of iron ore to iron. Did you know that producing just 1 ton of steel actually emits approximately 1.85 tons of CO2? So that's a very huge figure. The basic oxygen furnace also contributes to a majority of these emissions. So this is why it's important to decarbonize steel. First, it's to meet the global climate targets, like achieving net zero carbon emissions by 2050, and also to reduce the environmental footprint of the industries that rely on steel. So this paves for a more sustainable future. So this is not an industry challenge, but rather it's a global priority. So let's explore how steel can be decarbonized. So we have three green steel production pathways. The first one is the hydrogen direct reduction, which this method replaces the natural gas or coal used with green hydrogen during the reduction process. This results in zero carbon emissions from the reduction stage, positioning it as a game changer for sustainability. Then we have the electric arc furnace. So by utilizing renewable electricity to melt the scrap steel, the EAF significantly cuts down on CO2 emissions compared to the traditional BOF method. This process also supports higher recycling rates, almost 100%, making it both eco-friendly and resource efficient. And lastly is carbon capture and storage, which I'm sure you have heard about, which is to capture CO2 emissions directly from steel plants and then store them underground or utilize them later in another process. So it's particularly effective for retrofitting the existing infrastructure. So imagine that we already have a plant and we cannot afford to, for example, just completely change the whole plant to a different process. What we can do is add a carbon capture storage to capture the CO2 that's being emitted from that plant. Then we also have recycling and circular economy, which is important. So for the recycling, we know that steel is 100% recyclable when we use the EAF process, for example. So this is a very important part. So we need to use recycled steel, scrap, which can reduce emissions by up to 75% compared to producing virgin steel. So this significantly cuts down the environmental footprint. Then we have the circular economy concept, which focuses on extending the life cycle of steel products. So in this way, we reduce the waste and resource consumption. And then we should also design steel products with recyclability in mind to ensure that we can re-enter the production cycle at the end of their use. And this way, we are minimizing the waste. And lastly, for some statistics, today, 30% of global steel production originates from recycled scrap. So increasing this percentage could have a dramatic impact on lowering the global emissions and driving to sustainability. So recycling is just not about reusing materials, but we should actually rethink how we design these materials to ensure that they have a longer shelf life. All right, now let's talk about some industry and policy initiatives. So first industry-led initiative is the responsible steel certification. So this ensures that any company that's producing or producing steel needs to be accountable for the ethical and environmental standards. And also leading companies are now using green hydrogen and renewable energy to decarbonize the steel production process. As for the policies, we have policies like carbon pricing, green public procurement, and incentives. So I don't want to go deep into these ones, but just to give you an idea that some policies are being made to ensure that the steel production is going towards a cleaner path. That being said, let's talk about some of the decarbonization success stories. So in Sweden, they have this hybrid project, which is the world's first hydrogen-based steel making pilot, which showcases that a process can be actually achieving zero carbon emissions during production. So it's a groundbreaking shift actually from the traditional methods. Then we have the ArcelorMittal, which they have been investing in carbon capture technologies and renewable energy for the steel production plants. So this demonstrates that even the large-scale productions can be cleaner. And then we have the Japan's Course 50 program, where this initiative aims for a 50% reduction in steel industry emissions by combining hydrogen and also carbon capture technologies. So these examples underscore a powerful message, actually, that decarbonizing steel is not an aspiration or a dream. It's actually achievable through innovation, investment, and collaboration. All right. So the path ahead, first is to scale up the renewable energy to power the EF and the other hydrogen-based dark reduction method. So we know that renewable energy is getting more attention, and as this process for renewable energy gets cheaper, this would make many companies to invest in these technologies. We should also promote research in new steel-making technologies and see how we can improve our existing production processes. And lastly is to create financial frameworks to support the green steel adoption. So this is a collective responsibility. Governments, industries, and consumers must drive the transition to a sustainable steel industry. So with that, let us conclude our talk and see what we've learned so far. So first, we've learned that steel is very important. It's a fundamental material driving global infrastructure, automotive, manufacturing, and specialty products. Its diverse types and properties cater to a wide range of industrial and even consumer needs. As for the production processes, we learned the first process, which is the basic oxygen furnace. So it's efficient, but reliant on raw materials like iron ore and has significant environmental challenges due to the coal being used. Then the second method is the electric arc furnace, which is flexible, enables higher recycling rates, and holds promise for decarbonization efforts in the future. As for the environmental impact, we saw that the steel is actually one of the largest contributors to industrial CO2 emissions. So this requires urgent action to reduce its carbon footprint. As for the sustainability practices, we need to embrace innovative technologies like hydrogen waste reduction, maximizing the recycling, and improving the energy efficiency, which are the most important steps forward. And lastly, for the applications and innovations, we saw that steel is indispensable across industries like construction, automotive, and manufacturing, where innovation in the steel types is enhancing the sustainability and also performance. With that, we have reached the end of the talk.